Welcome to the show where you don't know if it's part of the show. Welcome to the show if you don't know it's part of the show.
Wait a minute. Wait a minute. You know, this is, excuse me, a damn fine cup of coffee. A damn fine cup of coffee. A damn fine cup of coffee.
Hello, hello, hello. What ho? Welcome back to another exciting and new episode of The Plain Truth. I'm your host, Travis Finley. This is Coffee-Sodes, episode number 9, but I think it's actually number 10 because I mislabeled them a long time ago. But we've got Good Times for All, or Zachary Zabala if you prefer. Too Nice for Rice, the man with a plan. What are your other monikers?
Oh, let's see what they give me. The Stay Puft Marshmallow Man. Some guy from the movie The Jerk, whatever Steve Martin's name is in The Jerk. They started playing part of it one morning, and I thought it was me talking. I was like, when did I say this? I don't remember saying.
I can't
So yeah,
remember. I can't remember what his name is, but
something Thompson maybe. But yeah, they've given me all. Oh, Stay Puft Marshmallow Man. They've given me all kinds of names.
all right, good. All right, so everybody out there, hello, Doc Michael, Ghost in the Prison, Rakia, Amanda with an H, Amanda, and there's TIU, and going up. Anybody else? Ryan Q's out there. So yeah, make sure you guys share the show so that we get some more people in on the chat, and we will open up a panel a little bit later after Zach and I have our chat. I think it's Zach. I think the point of contact for me to you this week was the show that you did with Cammy, wasn't it? Didn't I contact you after that?
I'm not sure which.
What did I say? Let me get into my text. I wonder because it's been a while since I asked you.
Yeah, things have been crazy. The house should hopefully sell here next week.
Okay.
I'm excited. I'm ready to get out east.
Now,
I'm going to be on the East
are
Coast.
you and Nodell's going into the same direction? Because you're supposed to be going to Karen B's next, right?
Yeah, well, that's where they're going to hang out with Karen for a little
Okay.
bit.
Okay.
So they pick a house.
Okay. Got it.
And I'm going to be staying with Karen. I'm going to be building
Yeah.
her a huge,
Yeah, dude. I actually thought about taking a couple days off and coming down and just hanging out with you, man. If I could do that, I
Well, I
totally
wanted to
would.
talk about that. When we get out there, we're definitely going to be doing the magnetic drop.
Okay.
And I
Yeah.
was thinking we could wait for a good time where you have a few days off and maybe you could come hang out and we'll have the spot picked and everything and you could be there for it.
Yeah. Okay. Well, let's see what that looks like. I think probably because I work Monday through Friday, I've got the weekends off. The weekend would be the best time that I wouldn't have to infringe on my paycheck. But
Yeah, and maybe we could even make it because if we really want to do it at multiple latitudes after we get it going, and
yeah.
maybe we could actually start up there by you. I don't know,
Okay.
make it easier for you.
Yeah, but it would be so slight that it would be insignificant. I mean, come on, really? You know, I'm just kidding. In the meantime, why don't you tell the audience what you mean by the magnetic drop? What are you talking about with that?
There was a guy back in the '90s called Boyd Bushman. He worked for Lockheed Martin. He was one of their head chief engineers. And just out of the blue, he had the idea, he claims at least, to take two magnets and instead of allowing them to, stick together north south, he was going to go north north and force them together. Big giant magnets. And he forced them together and bolted them together so they didn't want to be there, but they were, you know, it creates another pole, another magnetic pole. And he went to the top of the building, and he had 2 rocks that looked exactly the same, and he had the magnets in one and just a weight in the other. And when he would drop them, he noticed that the one with the magnets in it always hit the ground last by, there was, I think it was from 69 feet he dropped it. And he said everybody said there, he picked 9 people, just random guys that worked there. Nobody knew what was going on, and they all said, yep, this one hits first every single time. And he thinks it has to do with like counteracting gravity in a way by manipulating the magnetic fields and creating 2 south poles facing out or 2 north poles facing out, that it is dampening or quickening the drop rate. They say, according to mainstream physics, if you go south of the equator and do the test with the same set of magnet configuration, in the north, say if it's a north opposing magnet and you're in the north, well, that would be the south pole of the magnet. So it would attract faster. It would fall faster than the object, according to mainstream science. And then on the south end of the pole, it would fall slower because the north and north are then repelling each other. So it would make it fall slower. So this is actually a way to test to see if we're actually on a dipole magnet the way they say we are. Yeah, it'll be interesting. And the main point of it is to show that drop rates can be affected, by these magnetic forces, that gravity can be altered, manipulating magnetism. Yeah, buoyancy and density are what happens after all this stuff takes place. Like these forces are already there. They're always there. They've always been there. And then buoyancy and density is, an effect of these forces, but they cause things as well, if that makes any sense. Yeah, Ken Wheeler says there's 7 different things that account for gravity, and you can't take any of them out of the equations, or else, it doesn't make sense anymore. Yeah. Oh yeah, Tommy. Yeah, man. I love the stuff you're doing out there. I can't wait to get out there to go hang out with you at the flea market. Yeah, yeah, doing amazing stuff. Yeah, we're gonna try to get as many people. We'll make an announcement about it, make a big thing. Bob even wants to get the press involved because nobody's ever done this and actually like really collected data on it and got multiple angles. And I've only found 2 people who've tried to reproduce this, and it's both done with crappy cameras. One's done inside of a house, and the other one was done a little bit better. It was done in like a 70-foot fire tower, but none of them have really been done with a really good drop mechanism to where everything's falling at the same, where the weights are the exact same. So we're gonna really try to nail this thing down and get it out there.
Excellent. So, before we started the show, you were talking about having your brain tweaked by Ken Wheeler.
Oh yeah, with magnetism and incoherent magnetism. This is
this a new video that he's put out, or is it an old one that's been out?
No, it's a new one. He just put it out this morning.
I'll have to check that out.
Yeah, I don't want to get too much into this because I really haven't had time to think about it. It was just like an epiphany, but pretty much his cause for gravity is incoherent magnetism, be it, ever attracting force it creates. It never repels anything, incoherent magnetism. But when you create incoherent magnetism, you then dissipate the magnetic field of that object. once incoherent, it's like the polar opposite. Once you things incoherent magnetism is just a bunch of magnets that aren't lined up. They're all jammed together, and all their poles, the north-south, is facing in all different directions. That cancels out the magnetic fields of all those objects. So if that's what's taking place, then how do we have a huge magnetic field of Earth that can be read everywhere with a compass? Just a little thing that just popped in my head while I was in the shower. And
yeah, right. Yeah,
one of those. And I'm really gonna have to build on it. But yeah, I'm gonna run it by some people, and for some reason it doesn't make sense to me, the whole idea of them both being so powerful, because one means that you have less of the other, unless there's like a happy medium, kind of like a transformer. You wrap one coil over here and then you wrap 20 coils over here, and it amplifies that electricity, it multiplies it. But you can't do it like 1 to 1,000 coils. Eventually you start losing energy in there. So there's like a happy medium of how many coils to how many coils. I don't know. I think there's something to it. I don't know. We'll see. I got to run it by some people and think about it a lot more.
Cool. All right, so I'm scrolling back up to see what I posted I said, can you do a show with me this week? That was Monday. So I think that Cammy put out, oh, you know what it was? It was the talk that you guys gave, How the World Works. That's what it was.
Okay.
That's what it was. I had watched that again, and just really appreciated the information that you guys were putting out. So I'll try to remember to put links into the show notes for that video. But basically I said, oh, let's get Zach on this week, let's talk about this stuff, or whatever it is. And then you also made a comment about refraction and optics with some papers that you were reading. And so let's just kind of have an open-ended discussion. And
I can't find those papers, of course. That was years ago when I was researching all this stuff.
Okay.
But they were MIT papers where they were taking the curve of the Earth out of the formula and doing, point to point with different colored lights and measuring the different refractive indexes throughout different times of the day. And I'm not saying refraction isn't a thing, but the way people use it and think that you're going to see a clear object after it's being bent around the curve of the Earth, when you mix diffraction in with that and all these other things, and the fact that light bends depending on the frequency at different rates, you're not going to see a boat going over the horizon clearly. That's already over the horizon. There's no possible way. The different colored lights would be at different elevations, and then that would totally throw off your diffraction. That would jumble up diffraction so much. But refraction is real. It does take place. It really is. Did you know that time of day is very important when looking into diffraction, where the sun is overhead?
Well, yeah, I've heard that as an important variable in the discussion. Of course, I haven't put in the research in terms of that. You know what I mean? So it's like this is what I say. I might sound like a whiner to a certain extent, but this would take an immense research team. Immense. Yeah. Because, here I am. I'm the guy on the camera, right? So I've got 2 cameras going, and so I'm worried about my shots. I'm not thinking about the position of the sun. Mm-hmm. I'm not thinking about the air temperature, any of that stuff, So, yeah, I undoubtedly. And then what's interesting about that too, right? So if you have, let's say you have 2 consecutive days that are identical, except one is clouds, one is overcast. How would that change? So basically you've got the sun in the same position.
Well, yeah, they say overcast almost it takes away the diffraction or the refraction.
I remember last October shooting one of the clearest, amazingest shots in the Chesapeake that I've had. Just my Monet shot is 3 miles away. It's an historic lighthouse. That is
I know it well.
Mm-hmm. Yeah, and so it was overcast, and it was just everything crisp, clear, straight down to the shoreline, just beautiful.
Water temperature, air temperature was the same.
I didn't get any of that, but right, I see it that. But see me, so when I made my tongue-in-cheek comment earlier about it being so negligible in terms of coming up here to Maryland for a different latitude, the observations that I've made where I have paid attention to the wind or to the air and water temperature, it's like 5 degrees.
Mm-hmm.
It's not extreme. It's not this huge gradient that, so like you got a high pressure system and a low pressure system. If you've got a high pressure system and a low pressure system that are pretty much calibrated the same, you're not going to get a storm. But man, you cross that line where it's a drastic difference between the two, well then you've got the makings for a perfect storm. But 5 degrees, I just don't see, and that's what I mean too, right? So okay, so you would have to have someone studying how significant the temperature difference is, and then you would have to be like, okay, that's your job. That's all you're gonna do. You were gonna analyze the shit out of the temperature and tell us whether or not it actually makes any sense, makes any difference. Because when I have looked at the papers, and I mean, if you just Google refraction and miraging and everything like that, it's just as technical as looking up Andrew Thomas Young from his San Diego State University website. He basically says the same thing.
Mm-hmm.
So you can get that same information from Google, and when I see that, I'm like, this is not significant.
Yeah, exactly.
It's not significant enough.
I was doing research last night and this morning a little bit, and I read the same paragraph over and over and over and over, and even in the academic stuff, you have to go to where you're seeing people getting out in the field and taking measurements and getting rid of variables. Those are the papers that I look for, because the ones that are just on the topic, it's just a big parrot show. They're saying what they read in the book word for word.
Yeah, and so even I've done this. I think when I started doing my short series on the Vanishing Line, and I would go to just basic Google Wikipedia stuff on mirages, and they make these statements like Fata Morganas are most commonly seen up in the Arctic regions, blah 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 blah, but it can be seen anywhere. I'm like, well then what you just said, it has no significance. You can also see Fata Morganas anywhere. Like, well then why did you say that you can only see them up in the Arctic?
Mm-hmm.
Predominantly. It's just the information that they have for anybody who is trying to analyze this stuff. It just is not, I guess I would say, scientific enough, right? So because I'm not in the Arctic, and I've caught Fata Morganas on the Channel Islands. And it's a temperate, nothing crazy going on. The weather was really nice, 70 degrees, blah, 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 whatever, So it's not Arctic.
I remember that ship, where the hull of the ship,
yeah,
just like
I'm
disappeared.
trying to think
it
of
got real long.
I'm thinking of the Unicorn Freighter.
Yeah.
The looming Unicorn Freighter.
Mm-hmm.
Yeah, that's so good. I mean, yeah. Yeah, go ahead.
I was going to say, in that PDF that I shared with you, I had found something. I was just looking at that like about an hour ago.
When did you share it with me?
I put it in Skype and I think the Ether band.
And how long ago was this? I'm sorry.
Maybe an hour, half hour, something like that.
Oh, really?
Check.
I don't see it in...
Or I put it in Red Hen Radio, the old one.
Aye.
Yeah.
I see it. I see it. Okay. All right. I'll have to check that out. Okay. Thanks. Give me a second. I'm going to share my screen, and I'm going to go refill my coffee. And so, give me 1 second. Where am I going? Zoom.
Cool.
Zoom is here. Share screen. Share audio if we have it. And there's that. So this is the video that you're looking at is on the tail end of a massive Mirage event. But I'll be right back.
Yeah, I'm pretty sure I remember this video when he did it. We talked about it. That big dark band right below it, like, disappears. This is the same one I'm thinking about.
All right, I got the refill. Go ahead. What are you gonna say?
Oh, I was just going to talk to your audience about that paper. I was going to put it in chat, maybe.
Yeah, go ahead. Sure, have at it. Good morning, Ron. Good morning, Maria. Hello to everybody else out there. If you haven't said hello, make sure you just pop in and say hi in the chat. And yeah, go ahead, Zach, if you wanted to post something.
Yeah, let's see. I'm going to have to go find it again. But yeah, in this PDF, when it gets on atmospheric refraction, the guy's talking about the equations that they wrote. And he says how when you're looking at all this stuff, you could really imagine it as being on a flat plane or a flat Earth. By analyzing all the data of all the different refraction stuff that they've been recording, he says flat out that, yeah, just by looking at the data, you would think that the Earth was flat. But since we know it's curved, we have to throw these calculations in.
Right, exactly. Yeah, and that's an interesting. I mean, I would love to find someone who is an unbiased, and by unbiased I mean they're not in the debate.
Yeah.
They're not in the debate. They're in the field. I want someone in the field who has experience, but like, you know, say this guy that you're talking about, he's writing an article and he says, you know, by all, you know, what we're looking at, it looks flat, but we know, so then we have to then modify our calculations. You know, what needs to happen is that guy needs to wake up.
Mm-hmm.
You know what I mean? Because it's just that cognitive dissonance, that commitment to your interpretive grid. I mean, I know how difficult that stuff is to break out of myself, but I mean I have no rhyme or reason as to why the argument against Coriolis was all I needed, you know, to throw me into this whole fiasco. So yeah, so the what was the video that you did with? Do you remember what you titled it with your two your 5-gallon lids?
Diffraction Experiment 2, maybe?
Diffraction Experiment 2?
Yeah.
Let me see if I can.
I know it'll be in my playlist.
Is diffraction with 2 F's?
Yes.
Diffraction Experiment 2. Let's see if that pulls it up. Yep, there you go. Alright, so I'm going to pull that up. Pull that over.
It might not work as well. I know there's a lot of sunlight in the afternoon that way.
I hope I shared the right one with you.
As you can see here, it's really starting to get distorted a lot more. The mirroring effect's finally starting to kick in. Not nearly as much mirroring
Can you hear yourself?
as we had last time. Last time you could see the whole, both circles almost.
Yeah, I'm playing the video. Can you see the video playing on my screen?
Again, I'm going to have to look more into this stuff. That's it, folks.
Yeah.
The very last picture. Because I know it'll be different at the other end.
All right.
Make sure the camera.
Let's get this go along here.
Horizon today. Now, when I also did some pics with the lids, they did not blend nearly as much as the last pictures I
Nope,
took
this
with
isn't
the
the
lids.
one.
So today was another day that you could see much
Well,
clearer.
but you do have the lids on there.
One of
I
those
thought
good
that I
days.
saw the lids come up.
I actually
Yeah,
got
this
some,
is a
the thermometer
another
readings
lid
and
experiment I
humidity
did.
readings at both ends. From
Well, I just wanted
This
the
is the
picture.
one I didn't get
and
as
you
much.
can see
Okay.
what happened.
Okay, this is just
It is
the,
only about 78
this is
degrees
just the
down
light
here.
one.
Humidity right around 6.
Okay. So then, let's go back. So you had that, okay, one reason,
There you go, right there.
one reason
Yeah.
buildings disappear.
Yeah, diffraction.
Hello,
Okay.
everybody out there in YouTube land. Good
We'll
times
just
for
let this
all
play
here,
through.
or Zachary Zabala if you prefer. We are at work again, and I did a little bit something different this time. I measured that. It's an 11-inch piece of paper. I made a mark every inch. You have two lids here. One the circle at the bottom, one the circle at the top. And I was wrong about my measurement last time. It was not 170 yards. It was actually 160 yards down to that other end. Like an idiot, I took people's words for it. So I measured it this time myself. And from the lids here to the farthest marking that I take a picture from, it will be 153.3 yards away. I did that by 20 feet increments. I will be taking a picture every 20 feet. So tomorrow I'm hoping to get the exact height of what the Sears Tower should be, the Willis Tower, from this distance at this, to scale perspective. And we're going to see how much of the bottom gets taken off. But today we're just doing a little preliminary, and we're going to see what happens. So every 20 feet, I should be taking 23 pictures, I believe. And then at the end, I'll do one from eye height, which is roughly about 5.5. I'm going to have to get a tape measure out and see that one. But that probably won't be today. That'll be tomorrow. But yeah, I hope you all enjoy this. We're going to see what happens. Oh, and I also wanted to mention one other thing. See all these lights here? They're all the same height. You see them down there? All those lights, they're not getting any lower. It's all about perspective, people. It looks like these lights are going down, 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 down. And then they set over those, Nothing is setting, it stays the same height. It's all about perspective. And then once you get so low to the ground and so far away, you'll see what happens. So I hope you enjoy this. This is experiment number 2 with diffraction. And I'll see y'all down here at the other end.
God, I rambled so much in a lot of these older videos.
All right, folks. I'd have to say, all in all, this experiment went pretty well. I'm not going to take too much time on each picture. Not until around 200 feet from 1.5 inches off the ground do you really start to see some good distortion. I mean, you can see it earlier, about 100 feet, you can start to see it. If I would take that blue line out of there, it's a very slight minimum. It was a warmer day on this day. I'm learning. I've done a couple experiments on this since this one, and I was able to actually see more than this one showed. So I believe diffraction is caused by the amount of humidity also in the air. The more moisture and humidity in the air, the more it has to look through and the more the objects get distorted. And of course there's more humidity near the bottom, as the heavier water molecules and whatnot would be sinking.
Pause it right there.
You want to go back?
Yeah, did you notice how the mirage on the bottom grew in size?
Hold on. Okay, so let me...
Of course there's more humidity near the bottom, as the heavier water molecules and whatnot would be sinking. It's really interesting, folks, how all this works.
Wait, did you see it again? I don't know which.
Yeah, yeah. Watch below the blue line, the amount of the mirroring image that you get. It's real slim. And then when I go from that 120-foot shot to the next 20-foot shot, it like triples in size.
Okay.
Works how our eyes work. As you can see, the bottom is getting harder and harder to make out now, and they're starting to actually converge, the two circles that from the mirroring effect. The mirrored one.
Okay, I think I see what you're saying.
Yeah, that. See where there's that gray band on the bottom?
But the problem is that we're right on this one. You get a different level when you switch.
How our eyes
when you
work.
switch, watch. Hold on.
As you can see, the bottom is getting harder and harder to make out.
See how this raised up here?
Yeah, well, actually, go back one more.
Go back one more, like to
Yeah.
280. This is
A little
280.
bit more.
Go back.
Go back.
Okay.
Yeah.
All right. So this is
Okay,
right
right
at the
there.
beginning.
See how the line and then that gray line beneath it cuts it off real sharp. It's real small.
You mean this? You got a light blue line here. When you say gray line, what do you mean by gray line? You
The
mean
bottom, the concrete,
right here?
the flat. Yeah. See that between the blue line and that is real short.
Oh
And
no!
as
Yeah. Okay, so listen. This is the discussion that I've had on my channel. That okay, so in I'm gonna try. Let's see. The problem with sharing this, you can't see my Streamlabs stuff. So this is for the audience. So just listen to what I'm doing. I'm using a pointer to go through the discussion with what we're doing right here. So, the blue line is the beginning of the mirage. All right, it's called the vanishing line or the fold line. Okay, right? And then below that vanishing line, you have that section of the inverted image, and then that inverted image has a limit, right?
Mm-hmm.
Okay, so that limit I've called the disclosing line. So what I mean by that is that from the bottom of the image all the way down where it says 220 feet right now, so if you're down at the bottom and you know that you're looking at warehouse floor, you're looking at warehouse floor all the way up till you get to that line, okay? As you cross that line into the mirage, the warehouse floor is still there.
Yeah.
Okay,
Absolutely.
so what I mean by the disclosing line is that when that line ends and you see the physical warehouse floor, that what I mean by disclosing is that mirage limit shows you because this is so abstract, because you can't see behind the mirage. Okay, this is so, I'm sorry for being rambling like this because I'm just trying to think through this. So like these I'm totally like glitching out and geeking out at the same time because okay. The line that you're talking about with the warehouse floor is the horizon, and it becomes the curvature when ballers want to show us that ships are going over this curve, right?
Mm-hmm.
So that is the horizon for them. But
that's
what
the physical geometric
right?
horizon.
There's only one horizon, and it's geometric and apparent at the same time. The reason why I say that is because I've said all along, we need to get a team so that we can put someone on that location, as best you can. Like just right now, you could have someone in this warehouse go stand on that line. So, okay, let's go back. So, when you disclose something, you reveal it, right? Full disclosure, right? So the mirage is the obstruction. It hides the rest of the warehouse floor. There's no curvature here. The warehouse floor isn't on the other side of it going down. It's not sloping down. It's going straight ahead, just like we know it does in perspective. So where this mirage ends and then you see the warehouse floor, you actually see what's behind the mirage. So that's what I mean by disclose. I don't know if that makes any sense, but the vanishing line is where the mirage begins and begins to hide. The disclosing line is where the mirage ends and reveals to the observer what's actually behind the mirage. I hope that makes sense.
Yeah.
So I forgot the other point that I had come to my mind while while I was rambling.
Well, I was just saying with this bottom, the gray part.
The more it has to look through, and the more the objects get distorted.
Let me
This
I'm
will,
going to put you on mute on the YouTube.
yeah, that'll help explain the, like the different colors.
Okay.
You'll see the bands of water.
Yeah, the aqua bands. I call those aqua bands.
Yeah, the aqua bands.
Okay.
I think this is what's happening. See, as I get further away, the aqua band grew.
Right. So, again, this is all part of the discussion too, because if you want to geek out on sciencing refraction, I think that this mirage ought to be in the equation. Like, you should be able to science the distance that this mirage is going to cover. I don't necessarily think you can, but I'm just saying, if you want to throw us into, like, what are your numbers? Where's your tech? You got to predict this, buddy. You can't just...
You would, need markers going all the way down the floor.
Yeah.
You would have to measure exactly where
Right.
it happens at certain angles and how big it gets. And yeah, well, a lot of this has to do with diffraction. Like I was saying, this is your eye starting to mix up the information. The information's starting to get crossed right at the center point of your eye.
Well, what I liked about that last one was that I suppose, though, that's because you've got the top of the bucket lid on the bottom.
Mm-hmm.
So you've got a difference in terms of how it appears.
Yeah, I did that on purpose.
Right. No, that's great. This is a great demonstration. I'm going to go back up again.
And you'll see the hole on the right will actually look like a big oval. The hole on the bottom of the mirage and the hole on the top will look like one solid object once you get so far away.
Yeah. Right. So what's interesting too here is that the hourglass shape here is not so distinct here, but I don't know what that might be. Like, it's like there's something over here that's getting into the diffraction zone, because you would almost want a duplicate image on the left and the right should look the same, at least in terms of the shape of the diffraction that's going on.
Notice how the very bottom, just above the gray concrete floor, it's much more clear. And then as you go up, it gets more and more blurred until you hit that blue line. Like the bottom.
Yeah. Well, that's sure. Would we say that?
Well,
that's...
go to the left one. Look to the left. You can see that bottom circle right there.
Yeah.
And that looks almost like the circle above. But the circle that's out to the blue line is really distorted and has that big loop in it there.
Yeah.
So it's almost as the closer you get to the center line of your vision, the more distorted things are going to get.
Right. And it's a combination. It's not exclusively the physics of your eye. It's both the physics of your eye and light, and
and atmosphere too.
Atmosphere and perspective, everything.
Diffraction.
Everything.
Greatly, yeah.
Yeah.
Yeah, like it's just like gravity. There's probably 20 variables for this one though.
Right.
That's why I quit. When I got into refraction and trying to measure the atmosphere and know what the atmosphere is doing to get real, it's near impossible. They can't do it accurately. About 10 miles is the most they can do with the highest grade equipment they have. And they're somewhat accurate. I think it's like 70% accurate. And then as they get further distances, they try amping up the power and try new things, but they still can't. And then again, how do they know they're right? 70%.
Right. Well, that's the whole thing that, I mean, you would have to have
sensors everywhere.
Yeah, everywhere, because
you have to have like every meter a sensor, and then going up every meter for up to at least 30 meters. You would have to have all that censored out.
Yeah.
To understand what's truly going on.
Right. So
oh, check that out. Eye level. Once I raised myself up off the ground, I could see them clearly, and the diffraction pattern's gone.
Right. Yeah. I put a note in our texting yesterday about my warehouse floor, but I can't freaking remember where I put it. I hate it when I do this. I have so many files, I can't remember where I put it. Pretty sure it was...
Refraction is very real, but it doesn't always take place. There are certain circumstances that have to occur for a refraction to happen at a noticeable rate. Now, diffraction always takes place, no matter what, no matter how far you're looking. When you're looking at your hand, Fresnel diffraction is taking place. You can't see each individual cell. You just can't make them out. The lines are too small, too close together, and your eyes can't differentiate one line from another, and they all just blur together. That's Fresnel diffraction. Now, Fraunhofer diffraction is when you're looking out over water to like infinity, and that's when the sky and the water meet, and there's a band created across where they meet. That's your diffraction line, and that's where all the information gets garbled and things get mixed together. That's what causes the bottoms of buildings to disappear and boats to look like they're going over the horizon. It's just all that information along that line, the sky and the water, gets garbled. The human eye, 20/20 vision, 50 millimeter lens, 55 millimeter lens, at just 3 miles, 5.5 feet, will be taken away from diffraction alone. So at 3 miles away, you'll lose 5.5 feet of, 2.5 feet or 2.25 feet up and 2.25 feet down off that water line where it touches. You won't be able to make out anything. It'll all be blurred together. Just at 3 miles, 5.5 feet.
Okay,
and then you pull out a bigger lens and you zoom in and you see the whole thing again.
Okay,
that's why that happens.
You're bending my mind right now. I'm trying to think about it. I'm trying to think if I can bring something up that we can look at and we can talk through what you just said. Let me see if I look through this. Let me bring this over so people... I'm going to get rid of that. Drop that down. SE Montreal, what's going on? Shout out. All right. Thank you, Maria, for moderating. I hope that was because it looked like TIY was spamming the chat with some information. So I'll trust your judgment on that, Maria. Appreciate that. All right. Let me see if I can find something. How about we bring this up? All right, we'll just bring this up and see what we can do. That's a little bit... I don't like how blurry that is. Plus, I've got all those lines. Let's see.
Yeah, thank you, Trav, for putting in the hours, man.
I tell you, man, I love it as a hobby too. You know, if it wasn't, I mean, I don't know that I would have ever gotten into this at all, outside of the flat Earth discussion. But
nice to get out there, isn't it?
Yeah.
Just away from it. It's like a Zen moment.
Yep. I think maybe, let's see.
Yeah, I saw you did a couple more of your music of nature.
Yeah, God's music. Yeah. All right, let me see if I can find.
Yeah, I love those.
Hopefully, this will be clear.
Best medicine in the world, right there.
All right, so let's see. These are screen captures of a video, and so I guess what I'm trying to say, that if I didn't say it before in our discussion, is that what you brought up when you started to lower your, or you started to extend your when you were making those observations that weren't eye level, were you down flush to the ground? I can't remember.
Yeah,
Okay.
1.5 inches up the whole way.
Okay. So when you started first to move back and you started to see the image below the lids, you know, you made that comment about how thin it is, right? But it, but the abstraction is that image is obstructing distance. So if we would go back and reconstruct that demonstration that you did, I would mark out also, like you said, put out markers where that image stops, so that you could then see how much physical distance is being blocked.
Yeah, I can kind of see a line in this one actually.
The image that I have here.
2/3 of the way up in the water, just in the water part. Go up a little bit, right about there. Do you notice how the waves start changing, like size right there? It almost gets. I don't know. Maybe
I don't know about that. For me, maybe your eye is a little bit more of an eagle-eyed. For me, I would say that it's just blurry, but I'm not going to disparage. But let's go back to what I was going to. I think that was pretty good right there. That one had a little bit. Okay, so you know, where's the vanishing line here? You know, I'm being rhetorical, right? So, where's the vanishing line here? So the disclosing line is right here. So and so we know that there's water behind the mirage because perspective dictates that this water is extending into the distance.
Now remember, diffraction has to do with where your lens is pointed to. It doesn't matter. How do I put this? Diffraction will take place at the center. So if you draw a line directly through the center, top to bottom, cutting it vertically.
Here, let me do this. I'm going to open this.
Or horizontally, I mean.
I'm going to open this in Paint.
The center line will be your diffraction line.
Hold on.
And that will be where the mirroring starts to take place. Not exactly where the water, it doesn't matter where the bottom of the lighthouse is. It has to do with exactly where you're pointing. The center is where the diffraction line will take place.
Okay. So
do you understand what I'm saying?
I'm following you. I'm following you, but I want you to go back now that I've got the ability to. Oops, I want to draw a straight line, not a squiggly line. All right, so there's that. Let me see if I can make this any bigger. Okay, I can make that a little bit bigger. Okay,
yeah, can you measure from the top to bottom? How tall is that?
I can put in a grid.
Oh yeah, there is a grid on the side already. You have measurements.
Okay, yeah, but okay. Yeah.
Okay, a grid, yeah. So
okay.
It's 1,000. Yeah, you want to try and cut that right in half. That's where the center of your camera would be pointing.
Okay, so this whole image right here is about 1,400. All right? That's 1,000. 1, 2, 3, 4.
Yeah.
That doesn't look like, though, that if I put that at 7, that doesn't look like it's going to cut it in half.
Is it? Let's see. 1, 2.
That's not halfway.
No, each one is 200.
Each one is 200. Oh, I see. Because that's 200 there. So that's 2, 4, 6, 8. 1, 2, 3, 4, 5, 6. Yeah, but that's the same thing. I'm still in the same location. That's still 7. Because this is 2, 4, 6. Okay, hold on. 2, 4, 6, 8. So that's 1,800.
1,800, yeah. So
yeah, but then that's
about 900.
Well, yeah, but I'm still.
That doesn't look right either.
It doesn't. It doesn't either. It's because 900's down here. You're still gonna have. Let's just eyeball it. I mean, let's. What. Okay, hold on.
Yeah, what are with these measurements? That's messed up.
Okay, how many blocks are there? 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's just do it. That's 10, 20, 30, 40, 50. So we need to just go up here and go 25. That's 10. That's 25.
Yeah, it looks pretty cool.
Okay.
Look, there's a little line on the side that shows the halfway mark. Look at that. To the right, there's a little dot.
Right there, that one right there.
Yeah.
You got the corner right here. You've got midway. We're all over here. Oh, it's measured. Okay, yeah. Well, but see, that's interesting too. So we would actually have.
Yeah, and that's where I would have put it too.
I don't know though, because see, that's this. I would actually bring this down. Okay, well, what am I trying to say? What are we saying right here? This is the middle of the frame. That's what we're saying.
Yeah, that's
so the
where
middle
your
of the
diffraction
frame
limit starts. Yeah, and even look to the right of that dot. All the leaves on the trees above that dot start getting more clear, but right below it, they're all blurred, just like the mirroring image was on those lids that we were looking at. The bottom half part of it were blurred horribly.
Okay.
But we could see the top of the lid pretty good.
Okay. Say that.
Just put that line right on that line.
Up
right
here
on
at the
that
top?
dot. Where that dot is on the right.
Okay.
And go straight across over.
Okay. So, when you give your description right now, please differentiate between above the line and below, because I'll say
above the line. Now, if you were to go back to the pictures I took with the lids, above the line looks pretty clear, and you could make out just about everything. But right below the line, remember how everything got stretched and distorted and bigger and shaped all funky?
Yeah.
That's what's happening right there. And then there's another line in here in the water somewhere probably that we can't see.
I see. Okay.
Cut that off.
Okay. So I guess my question would be, how significant is that information to this discussion? Because it might be like a different nuance of something, of a different focus point. But let me talk through this to a little bit right now. So the window on the lighthouse here. Now that I'm thinking about this, I want to find. I would have to have a contrast shot, right? So here's a contrast shot. And again, this is video because it's not going to have the focal length. So I'm going to put that in the back pocket real quick. I'll pull this one up just for random contrast. What I'm thinking right now is I took a shot of the lighthouse standing right in front of it. And I've just got to try to remember where I put that, because what I'm trying to tell you is that I don't believe that this is to scale. So this light, if you were standing in front of the lighthouse, this light would actually be closer to the top. This lighthouse is only 34 feet tall, and this light is about 2/3 up. Okay, so if you were gonna think along those lines, if you knew that this window, okay, so if the lighthouse is 34 feet, and let's say this window is 14 feet lower than the top, right? If you think about this in abstraction, then that this represents 14 feet, which would then mean that let me see if I can do this.
Oh yeah, I'm not saying that's the water line or anything.
No. I know. I'm trying to talk through the craziness that's going through my head right now. Okay, so let's even this is cropping it a bit because the top of the lighthouse extends past the frame of the picture. But what I mean is that this lighthouse is, like I said, 34 feet high. Now, if we knew that the window was 14 feet lower, and we marked this, so this box then is now 14 feet. So then if we drop this down, this now represents physical distance from the light, or from the window to the ground. So, but this is only 14 feet, but we know that there's 20 feet missing. So then we have to extend this down, and now this is 20 feet. So now this box represents the physical dimensions of the actual lighthouse. This is where the ballers get their crazy cut and paste blink test bullshit. Because you can't...
Yeah, this makes sense, though.
What makes sense? Go ahead.
The bottom part, I mean, it's physically there, but like we saw on the warehouse floor, all that stuff gets so distorted. Just like we see the water bands. Those are that's a distortion that we're seeing.
Okay.
So yeah, probably down to there, I would say all that water isn't really, that's not really there.
Okay.
That's a big giant distortion.
Okay, yeah, I agree. But here's where I'm going to bake your noodle, hopefully, or possibly. This represents where the true dimensions of the physical lighthouse are, right here. So that line right here, this is ground level. Okay? And I think that we can say that safely because, let me leave that there, put this up here. Because if we bring this here, and then this here, we have an obtuse angle. Okay, so that shows us where the vanishing line for the lighthouse is. Okay? So my point is that there's no way that this is showing you the actual scalable dimensions of this lighthouse, because the window physically is closer to the top, so the window should be up here if you think in terms of one-to-one scaling. So what I'm saying is that this top is stretched out higher. It's like how we used to play with silly putty in the comics, right? You put the silly putty down and then you stretch it. That's what's going on here. But the bottom part isn't proportional. That's what I was saying before, that if we were making this the true dimensions of the lighthouse, this is why ballers think the boats are over the curve. They think that the boat is physically down here when all this shit right here is compressing the image.
Mm-hmm.
And they just don't think along those terms. So
they're stretching the image even.
But like I've said before, right? Everybody out there in the audience ought to know there are multiple effects happening at once. In my opinion, multiple effects.
Sure. Well, yeah, the atmosphere it's a fluid. It's like a mixing, swirling garble of a bunch of different. Trying to say that everything is happening from the right side of that building to the left side, the same, between your distance, you can't do that.
So here's an interesting contrast here. This white smudge right here, inside this box, this is a flagpole. And so I would think that the default of someone looking at this is that this is an entirely physical object all the way down. And then, so you have the water ending here, and you have and now again, if you knew, right, like me, okay, I go into this not knowing anything. I don't know what I'm going to find, but I know when I start over here, I know that this flagpole is on the ground, and it's about 60 feet off of the shore at an elevation of 10 feet. Okay? So if I know that this flagpole is on the ground, and then I come over to the other side of the bay, and I take this shot, and I have an initial thought that this is the physical light post, or flagpole, I'm going to think that the ground level is down here. But it's not. It's up here. And so this whole thing right here, this blue arrow here, then let's go back to the start point of what I was trying to flesh out with what you said in terms of what happened when you moved away from your lids and you started to get this expanse of the reflection or the mirage. What physical distance does this inversion represent? That is,
I think that has to do with atmosphere as well, because
yeah. Go ahead.
the whole diffraction thing, the way they did Rayleigh's criterion, which is the mathematical formula for figuring out diffraction of a certain size aperture, it was all done in a perfect nitrogen oxygen based atmosphere. There was no dust particles, there was no moisture in the air, it was 0% humidity, perfectly clean air, and
completely irrelevant then.
Yeah, so exactly. Well, that's why they call it the limit, because when you add atmosphere to it, it only gets bigger. So this is the limit. This is the best you will see. There will always be this amount cut off, and most likely more. But this is the limit. So when you're looking out 3 miles with the human eye, 5.5 feet, no matter what, will be cut off. Now, you add atmosphere and dust particles, all that kind of stuff into it, that thing only gets bigger. The cone, it's like a cone. It's based on angles. So it's looking out from your eye, and then it goes out like a pizza slice with the point tipping it right at your eye.
Yeah.
And the more atmosphere particles you get, dust and water molecules, that pizza slice gets wider. Okay. So you'll only see, that's why they call it the limit. This is the best you can see in perfect conditions, with your aperture being this size. That's what that calculation is based on. So when you throw atmosphere into it and refraction and things like that, all these other things, it just makes your visibility that much less along that line. That's why I was telling you to try to take pictures pointing directly at things, and then take pictures.
Right. See, but then again, that's the right. So that is that's a task. So we would have to have.
You need more.
We would have to have 100 cameras. We'd have to have 100 cameras. Okay, your job is to take these images and move your camera lens up and down. I did that. I did do that a couple of times, but I have no clue what folder they're in. Okay, so let's go. So my question. This is where I start off, right? So you see that yellow dot. That's me standing on the beach. This is the lighthouse, 5.7 miles away. So because we could put a boat on this location right here, that's the let's go back. That's the geometrical horizon. Okay, I mean, it's just stupid. It's the horizon. Okay, you can get there. You can get there. We can't on this day because it's gone. It's in the past. So, but this has a physical location on the Chesapeake Bay. But my question is, where the it could be right here. It could be right here.
Mm-hmm.
It could be right here. So
in the Black Swan photo, you see the further out you're looking, the more compressed it gets.
Yeah.
So
let me pull up something just to jump around and go crazy with all this stuff. Go ahead, keep going.
So yeah, when you're looking at it as a 2D picture, and 1 inch up represents, however far, we'll say 2 miles. And then you go 1 inch up from that, that's going to represent, however, that should be a mathematical formula. Someone needs to figure that out. You go up 2 more inches, how much distance is that next 2 inches? Because it's going to be a lot more than just the 1 inch. The first 1 inch of the water is 2 miles. The next 1 inch of the water you're looking at.
Right.
5 miles, 7 miles.
Yeah. Okay, I'm trying to find. This is so frustrating because I think that I am being meticulous by okay, I just made this file. I'm going to put it right here so it's always here. See, I had done this with, I had wanted to do this with Sean G. Now I got to think about what I would have labeled it if it's not in the folder that I'm thinking about. This is an Etherband tutorial. I had one platform side by side, and I just want to make sure that I'm not overlooking.
It's got to be
it.
so hard when you have so much of the same. I've never stayed on a topic this long as you have and put in this much work.
Oh yeah, well, that might be because you figured it out faster than I have. I'm just slow to. I'm slow on the draw.
Well, no, I just gave up. Once it came to the atmosphere part, I was like, I started looking into it, and the equations use like every letter of the alphabet and then a bunch of symbols plus. And it's like, yeah, I'm not even gonna attempt to look at this.
Well, I don't know
They look like nonsense.
I don't know where the heck I could have put this picture now. Maybe here we go. Nope.
I did write an equation though for the limit. Have you ever seen that?
I think I've heard you talk about it, but I don't think that I have seen it. Did you create your own language, or did you use?
No, it's all real equations, and I just put them together in a formula.
I found it. I'm sorry. Do you have that available right now? Can you pull it up to?
Yeah. Let me. I know I have it on that video, and I'll just take a screenshot of it. I don't want to go looking for it.
Do you mind if I throw out the link and see if anybody wants to come in and stir up the pot with us?
No, it's cool.
All right. Let's see. This is that.
Wait, what was I looking for again now?
Your formula?
Okay.
All right. I'm gonna throw this link out, everybody. Alexander, SE, if you guys have the gumption to join the panel, here's the link, and then we can just have a fruitful discussion. So, thanks once again for Zachary, Zabala, or Good Times for All, if you prefer, for being here, being a repeat offender on my show.
Yeah, I always got time for you, Trav.
Always a good discussion, man. So
there it is. Okay, hold on.
All right, so if you want to pull it up, I'll stop sharing, and then you can share.
Oh, I got it. There we go.
I'm gonna be right back. I'm gonna freshen up my coffee.
Oh crap! How do I... There we go. I've been listening to a lot of Alex's True Sophageo. Bob is always playing it in the background, always working.
Playing what?
Alex's True Sophageo.
Oh yeah, yeah.
I love that album.
Oh, it's so good. It is so good.
Yeah, I just threw it in that Skype, in the Etherband boy.
Oh, okay. You want me to share it? Okay.
Yeah, I'm on my phone.
All right, no worries. All right, so let me go back to...
It's weird. I have a computer now, and I still, whenever I'm live, I'm always on my phone.
All right, so I'm sharing my screen. I'm opening this image. All right, so you can see that?
Yep.
All right, so talk us through this.
Okay. The top one is Rayleigh's criterion. that is just converting your radians, or that's finding your angular resolution limit of your lens. So you get lambda is your wavelength of light.
I'm sorry, let me stop you.
Yeah.
What is radians? What do we mean by that?
That is another, I think they made that to mix people up. It's another way of saying an angle. It's just another type of measurement for angles. And this is converting your radians, radians into degrees.
Okay, go ahead.
So, or this is taking your measurement and turning it into radians. That's what Rayleigh's criterion was based on, was finding the radian. So your number of radians equals 1.22, which is your atmospheric distortion, a perfect nitrogen, oxygen-based atmosphere, times lambda, your wavelength of light, over d, the diameter of your aperture. And that is what gives you your angular resolution limit.
So lambda represents a static, uniform measurement of light wave.
Yeah. It's just whatever light wave you want to throw in there. L is considered just your light wave. Whatever light wave you want. And D, same as diameter of your aperture. It could be whatever. Yeah. That's why they just give it a symbol.
Okay.
Lambda really looks like the, what is it? It's like a squiggly line with a straight line coming down to the left. The lambda sign.
Yeah. No, I know what a lambda looks like. Yeah.
So it's just another way to say this is your wavelength of light. Whatever wavelength of light you're choosing, you put it in here. Okay, and the next one is
go ahead.
Turning your degrees, into radians, or your radians into degrees. So you found your radians up there at the top with your angular resolution limit, and now we're turning radians into degrees.
And the x is the function of a parenthesis. It's the multiplication.
Yeah, that right? One is. Yeah, capital X is more like X number of degrees equals radians times 180 degrees over pi.
Okay, I just wanted. Yeah. Okay.
Yeah.
Got it.
And then the next one, I'm just breaking it into 2. X over 2. I'm just dividing it because you see, when you're looking out, whatever is distorted on the top, if you look to the picture on the right, you'll have as much distorted above as you will below. So we're breaking it. You don't need to do this when you're working with short distances, but once you get above like 250 miles, which nobody ever does,
right,
this would be required. So I just threw it in there. It doesn't affect it on the shorter distances. It's not only until you get to really high distances does this come into play. But mathematically it's more sound this way. And then you're just finding
what would this be useful for in observations that I make? Let's just say, for instance, how would this be helpful?
This will tell you how much will always be cut off due to your limit of optics. So you have a lens this size with an aperture this size, and you're looking at X distance and you're trying to see something this high off of the horizon. This X amount will not be visible along your line of sight. There will be a blurred no matter what. This is your limit. This is where I get when you look 3 miles out with the human eye, you will always have 5.5 feet cut off. This is the equation that does that.
Okay, so again, this to me is a clinical equation. So, yes. Right. So then if
it has nothing to do with atmosphere.
Right. That's where the fun begins.
Yeah, I couldn't. Yeah, I got to this point and I was like, okay.
Yeah.
How do you stop the atmosphere and take a picture?
You just do what Rumpus does. You just draw fucking diagrams and say, now we know where the geometric horizon is in a world with no atmosphere. We're like,
exactly.
Except for the fact that we live in a world with an atmosphere, so just throw that out. Oh no, we can completely make up this shit and give you an equation that's based on a world that doesn't exist, and then tell you that represents the reality in which you do exist.
yeah, that's why I gave up at this point,
Yeah.
because atmosphere it's a fluid. It's a
Right.
never-ending
Right.
swirling cycle of nonsense that you cannot quantify.
Now, did you throw that equation out there for anybody to mess with and to kind of validate or anything, or not
I
that you
ran
had to?
it by
But
a few mathematicians. Gav,
yeah.
he said he thought it was sound. He'd like to do some testing on it and this and that. Just because the angles change. A lot of people think if you double the distance, it will half the angle, and that's not the case.
Oh, so like
There's
almost the what's that? The inverse square law.
inverse square. Yeah, that's not how optics work. I mean, you can put it in AutoCAD and lay out a bunch of lines and then draw, and measure the angles to each set of lines, and they don't half each time the distance doubles.
Right.
It's
right.
very close. It's very close to halving, but it isn't exact.
Okay.
And once you start quantifying things, numbers start to build up.
All right. So back in our discussion, you said something that triggered my thought of this image. You brought up the Black Swan. I don't know if we can go back and recreate that concept, but here's the same oil platform, and you can see that it's about 7 months apart. Is that the 4th and the 11th? Something around, yeah, it's like 7 months apart. Same focal length, same beach, same location. We've got, a pretty clear shot of the feet.
Mm-hmm.
It's still refracted. It's not. I mean, you can see definition, but it's still blurry around the edges. So I'm still, there's refraction going on here. But so we have the horizon here, and if we, in my opinion, I mean this, I actually think that the horizon is here. It's so that if you follow that line, and then it's behind this. Now this is a tough one to go back to. I would have to probably go back to this file date and see if I have a video of this at all to see if I can look at this. But in my opinion, when you have a blurring, so you've got these aqua bands. Here's your darkest, thickest part, then the next one, then a real thin one, and then this one right here. Okay, this last one right here, in my opinion, when you have a distorted image, it's because there's something physically there. If that makes any sense.
Yeah, it looks like it. Yeah.
So if we put this line right here, I don't have it measured up exactly to this horizon, but if I did, this whole image would drop down. But you can even see right here that that this image is compressed.
Oh yeah, big time.
You don't have the spacing between the feet here. But anyway, we started talking about your formula along the way, and what you had said.
Yeah, those almost look like they're at totally different elevations. Like the one on the left is way lower.
Exactly. Dude, you're singing my song, right? That's exactly what I say. This one looks like I'm close down to the water, and I'm closer to the water and lower down to it, and this one looks like I'm higher up and farther away. Yep. That's 125,000% the Aether band, dude. That's what throws Sean G off. That's what they're like. You are not in the same position. I'm like, bro, trust me. Trust me.
Yeah, that's wild.
But let's go into the video that I played the other day. You okay on time?
Yeah, let's see. I got about a half hour more.
Okay. So I played this 2 days ago and did some analyses with SE Montreal, and Alexander Lightwater came in. Alexander's out there. I don't know if SE's still there. Alexander's in the chat too. So shout out to you guys. This is a video by someone up in, I think it's Denmark, and this is the turning torso. I don't know if you're familiar with that landmark.
No.
Okay, but so he's showing us where he normally shoots from, and he had to adjust his setup because this cruise liner was in the way. So we've got this. This is kind of like the shot across from North America to Canada. What's that one? Jenna Fredo did it. What was that?
Yeah, Toronto.
Yeah, yeah. So we've got this twisting torso. This building that twists. And one thing that I thought that you could help think through comes toward the latter part of it. But I want to try to play through this right now because I'm trying to rethink what I saw later on. So again, if we're taking it for granted that this image is taken from the same location as what happens later on in the video, then we have a conflict of data. Because we have this huge ship right here. Huge ship that is cut in more than half, I would say. So we've got these stacks or whatever this is. We've got the captain's deck here, but we have no hull.
Well, we gotta know what kind of ship it is. Some of the barges don't look like they have a hull at all.
Oh, that's true. That's true. Yeah.
Lake Huron is very shallow.
Well, this isn't.
It's only like.
Yeah, this is in Denmark.
Oh, okay.
Yeah. I was just using that as a contrast in terms of looking across water at a large structure, like what Jenna Fredo did. Okay, so what we're going to see though in the next image is we're going to still see this turning torso. We're still going to see this shoreline. I'm just going to call it a shoreline because it's lower than the building and it's closer to the water than the building is. But think about what we're looking at here, okay? So kind of like what you said a moment ago with the water looking higher up and closer. I think that we might keep that in the back of our minds when we see the next image, that we're going to see a difference in the way the water looks because we have a approximate image here. This boat is closer to us than the shoreline, and it's huge. So, the other thing is that this is 15.5 miles away, to like 25 kilometers. And hey, Cynical Skeptic, how you doing? Hunter Thompson. Anyway, think through what we're looking at here. This is being purported as curvature. This horizon is curvature because it's blocking this boat. So we're going to get to the next part. I'm just going to play it out just to see if I catch something that I missed before, so I apologize if
no worries.
It gets tedious. Okay, so you're going to see a lot of the same landmarks. You're going to see this church here in the next one. So this building was crazy distorted. This like if you're looking at this right here and you see how wide whatever section this might be, you think that this is huge. In the next
is this video or a time lapse?
He says, well, this one here is time lapse. Let's see if he goes back. Let's see. Hold on. To me, this one looks like video. This one looks like video. The next one is definitely time-lapse because he says in real time as the ship goes by. So he's saying that this is real time. So to me that this is just straight video.
Okay.
Okay, so this is the ship's gonna go by, then he's gonna switch to his time-lapse. Would almost have to take a screenshot to have this as a control for the next one. Okay, but now you can still see the same church, right? So he's set up in the same place. Okay, but now we have a larger section here. Remember that? Look how thin that red section was right here. See how thin it is there? Look how thick it is right here. See that?
Wow.
So then here it's completely smashed up. So now, to the untrained eye, they're going to think that this entire column, or let's do this one, they're going to think that this entire column is physical. And it's not. You cut it in half, and you've got your shoreline, which then means all of this below that is physical water that you can't see.
Yeah, that mirroring stuff that we see.
Okay, so now we got time lapse. We've got a boat going across the horizon here. But now, if you think, well, if you think back to, again, I would have had to have taken a still shot. This is so tedious.
Notice all that distortion is happening below that halfway point.
Look, you just had this sailboat go by. Watch the. Sorry. Okay, so we've got this boat going. We don't even know what that is. I mean, it's a boat, obviously, but we don't know its dimensions. But it looks to me as though... Let me see if I do this. Oh, that goes forward. I wonder what the backward... What's the hotkey? Alexander, what's the hotkey for going backward frame by frame? Let me see. Hotkeys. Preferences. Hotkeys. Alright, so E, there it is. E is next frame. So why don't they have a previous frame? Short backwards jump. Very short backwards jump. Shift left. Let's try shift left. Oh, that was a bit more backwards jumpy than I wanted. I wanted just a frame. All right.
Yeah, they have forward frame, but not backward.
Right. It might be there, but so okay. So now you've got this image right here, so you can see this dark wedge-shaped thingahoozy. But then you've got this lighter band underneath it, which, in my opinion, is the inverted image of whatever's above this right here. Okay, so you've got a fold line right here of whatever this is. So again, you've got multiple fold lines here. You've got this horizon, and then you've got the boat here. This boat is not physically on the water down here. It's physically on the water up here. And this goes back to our discussion in terms of what is the distance between this location and where this boat is. It could be 2 miles. This boat could be 2 miles away from this horizon. But it's not over a curve. It's prospectively in the distance. Okay? And so now what I noticed coming up here is we're going to have this, okay, so look, we've got this catamaran here. We're going to see a mast come across the screen. Let me slow this down a little bit. Oh, there, was that it? Yeah, that's it right there. So there's something right here. So let me back up. Yeah, I've got to figure out what the backup is. What the jump back is for a short distance. I mean, I love this. I absolutely just love watching this and just amazed by it.
What the hell is going on? Yep.
Okay, so I'm going to just kind of push the space bar because I don't know that I saw when that... Here it comes. Here it comes. Okay, so right now it's right here. Right here where my cursor is. So I don't think we're going to be able to see a very good until it gets into the darkness. Alright, so now my VLC is glitching. Okay, but it's right here. So it's going straight across. We have no idea what that is. None. No clue. I mean, it's very thin, so it's possible it could be the mast of a boat. This whole thing's glitching.
Wow, that is wild.
All right, so now we've got a sailboat right here coming across right here. Again, it would be a mistake to think that it is physically on this location right here. But what just caught my eye is this level.
Yeah, that's what I was looking at.
The level right here, so let's back up. Look at that.
Look at the red line. Look at the red line to the right.
Right, right. Okay, so I'm gonna put my pointy finger in YouTube here real quick on that line. See that what needs to happen is see, I wish that I could share with you what I'm doing on Streamlabs. But if I bring Streamlabs over to the window that I'm sharing, it's going to do that Twilight Zone dimension zap thing where it makes all of these windows go off into the distance. You know what I'm talking about?
Mm-hmm.
But anyway, so let's look right here, right? Let's look right here because I think that there are 7 of these divisions. 1, 2, 3, 4, 5. There's another one right here that we can't see. So let's watch this.
It'll pop up though.
Yeah. That's what I noticed too, right? All right, it's very, very subtle. Very subtle. This thing's hiccuping. Let me see if I can close a window down. I'll close Skype. I'll close... Oh, that wasn't even open. I just opened it. Let's see. I can't close anything else down. I'll close down Google Earth. We're probably going to be done with that. All right, let's see if this helps. I gotta go
right
back.
there.
I gotta go back because it glitched and then it jumped. All right, so we just barely see something developing right there. Ay.
Yeah, you'll notice when that red line gets real big, it
Yeah.
comes into view.
Look at that. This is Skunk Bay. Awesome.
Yep, right there. You can see it.
Look at that. I mean, it's like this. It's like where was this section of the building a minute ago? Behind here? Was it behind these buildings? No, that was total compression.
Yeah.
Look at that. That is crazy.
And that red line to the right just gets thick and then thins out. Look, it's like waving at you. That is wild.
Yeah, I mean, this is great footage. I'm going to put this at regular speed because I think the slowing it down makes it glitch. Let's go back again. Let's watch that again. Okay, again, there's that boat or whatever that went across right there. So again, if we're going to go on the fact that this is an inverted image, which it is, this right here is going to represent at least the shoreline that we can't see.
Mm-hmm.
So then if we take this all the way over here to whatever this is, this vertical image right here is not 100% physical. Half of it is inverted image. So it's not sailing on the water here, it's up here. And this is so simple. Absolutely simple. Alright, so here we go. So here, now we got this. So, okay, so right, so it would be interesting too. This guy has a lot of footage on the twisting torso, and I don't know, but I'm just gonna say each of these sections I think is symmetrical. I think or proportional. That is, that there's 1, 2, 3, 4. There's 5 floors. 1, 2, 3, 4, 5. look at that ronk.
Yeah.
You know what I mean? So it looks like then this is 5, this is 5. But you can see visually right here, if these are both 5 floors, this is bigger than this.
Mm-hmm.
You can't tell me you know what you're doing. Okay, so
It looks like Dr. Seuss buildings.
right, yeah, right, yep. Okay, so this is let's say 10 feet per floor. Let's go 60. Let's say 75 feet. Let's just say 75. This is 75 feet. This is 75 feet. 75 feet. 75 feet. 75 feet. And then we got another layer down here. But let's go back because that layer is gone, right?
Mm-hmm.
Okay, but now once I push play, you're going to see this line come up, and then you're going to see another floor appear.
You?
Look at that. That is absolutely gorgeous. That is absolutely gorgeous. Yeah.
So much going on there.
All right, so now he's got a distant shot here. Okay, and this is what I spent some time analyzing Tuesday. I got a comment here. Sorry. Oh, here's Matthias KP. This is the source channel here. He's in the chat. Zach.
Oh, great stuff, man.
Let's see. So
thank you for putting in the time.
All right, so Hunter Thompson says, where in the equation he presented is the variable for the ether band? Yeah, that's Hunter. Zach said that's when he threw the towel in. when he
when atmosphere comes into it, there's good luck with that.
Yeah, he said, I'm done. Tapping out. Okay, another question for you, Zach. What happens to your equation when you look up slightly? Right, yeah, you mentioned this. What happens to your equation when you look up slightly or up at a plane? Does the plane vanish bottom up? Just curious.
Well, no, because there's no land there to distort the image.
Yeah.
I mean, eventually, if the plane were to just keep flying away,
but then the resolution
straight
of your
away
eye
from you into space, it would disappear.
Yeah, but then you're losing the resolution of the plane because it's going farther away from you. So then you have a completely different optical effect that is at play. Okay, well, Matthias KP, thanks for being here in the chat. And he says that the segments have the same dimensions. There are 9 total. Matthias, if you're interested, let me know if you want to join the panel. Alexander is joining here. Okay, so here comes Alexander. So Matthias, again, if you're out there in the chat, just tag my my channel and let me know. I'll put the link in, and then we can have you be a part of the discussion. Although I do need to wrap up probably in 20 minutes, which means I won't wrap up until 40. Okay, so Alexander, are you there? I let you in. Hello.
Yeah, but I have some issues. I'll contact.
Okay. Okay, so Zach, here we have a the same observation, but zoomed out. So we have more in our field of view. Now, I am interested in your input right here. Can you see where my mouse is?
Mm-hmm.
There's going to be a kind of like a warehouse floor 5-gallon lid demonstration here, whatever this is. That caught my eye the other day, so I'm going to push play and see what happens. You can see it dancing right there, right?
Mm-hmm.
Okay, so you can see it go together. Like, there it is, it's together. And then you just see it flip.
It's gone.
Yeah, and then look how far away it is here.
Wow.
Right? And then you've got a line. See this dark line that comes up right here. In my opinion, this is the shoreline. Because of what I've seen in my footage, this is the shoreline. And then right here we've got a boat that is as high as what I'm suggesting the water level to be, right? And it's right there on top. It's got an inverted image below, and right between it you've got this dark band. And then you've got this boat.
Yeah, I see an inverted image all the way across.
Right. Yep. Yep.
Travis, you don't have the same picture in YouTube as in Zoom.
I don't have the same. Oops. I need to get my pointer out of the way.
You are in Zoom. You are in Nordhaven, and in YouTube you are still on these round objects of Zach.
Really?
Or did I?
Let me pull up my YouTube real quick.
Or did I? Oh no! Sorry, that's my fault. That's my fault. Sorry.
No worries. Nope. Appreciate
I
that.
do that all the time. I'll pause it and be like, "Hey, what's going on? Why are we still on that?"
So Alexander Lightwater, meet Zachary Zabala. Zachary Zabala, Alexander.
Hello,
Nice to
Zach.
meet you, Alexander.
Yeah. Thank you. You too. Great fan of yours.
Oh, thank you. I'll do what I can.
Alexander, did you want to say anything before you forget, or
I wanted to say that the greater the distance, it's rather low at the surface. The greater the compression of the surface, the less details, less height differences. And the closer the viewing angle gets to zero. So with a smooth surface and a view angle nearing zero, you can get a mirroring effect, right?
Absolutely. Yep.
Yeah, that's the great insight I got from your bumpy road, Zach.
I was hoping that would touch somebody. Thank you so much.
Yeah.
Yeah, that was all the videos I think that are going to be like the most astounding and wake up the most people. Nobody gets them. So thank you for that one. Yeah, you're the only person who's ever mentioned that video to me.
Yeah, I already made I sent a mirroring email to Travis one time with the bumpy road.
Yep. I remember that. Yeah. I'd have to go back and look at that again because I... a lot of the times when I get that stuff, I'm on the road and I just don't remember to go back and look it over again. I remember seeing that email. I'll have to go back and check that out. Maybe what we can do, Alexander, next week, we can actually, let's use that as a show. That would be good. That would be good.
What?
I'm sorry?
You use it as a?
Use it as a show. Let's do it for a coffee-sode. We'll go through that email.
And my refraction ideas, because when when you had your talk with Greg, I realized myself something about data.
Okay. Excellent.
About Andrew Young thing. Yeah.
Yeah. Good. Fantastic. That's what this is all about. Great. Okay. So I kind of backed up a little bit just to see. Okay. So let me do this contrast and blow your mind, Zach. If you haven't seen this video, let me see. Do I have a? Okay, that's that. So let me go back here. Let me see if I can find the recent crazy ether. Okay. Okay, so this black band here, in my interpretation, is the physical water. Whereas I think most people are going to think that is the mirage. This is a mirage. No, the mirage is right here. Okay, so you see this color differentiation here, small. Here it is, stretched out.
Yeah, just like the lids.
Yep.
The bottom half.
Right there. That's a good one right there. Oh, Alexander, did you hear me ask? So E is just jumping forward by frame. Is there one that goes backwards just by frame? Very small, very subtle.
As far as I know, not no.
That's a problem. Okay, so here we go. Look at this. Look at that. That's interesting. So you've got this land here. I mean, like, is this? You see this this inversion here? Is that this?
Yeah,
possible.
And it looks like that. See that? You can even see the wave in the top half. It's very slight, and in the bottom half, it looks like the Pepsi symbol.
I don't see what you're talking about.
Okay. Go down just a hair. That wave right there, the black to the white. See that curve?
Right here.
That S curve in there. Yeah, you can actually see that in the top part.
That's
just barely make it out.
Okay, that's again. You did that before to me. You're making me feel old because my eyes can't see what you're seeing. But yeah,
you can just make out that little S curve in the top half. It just curves a little bit, but in the bottom half, it's very pronounced and stretched.
Okay. All right, so here, this image here is duplicated down here. Here's the sky from up here. Okay, so now we've got this is platform Grace. This is a towering image, right? So this entire image here is mirage. It's And what we're going to see is this entire image is going to be replaced by the physical water that's there. So this comes into what I've said before, like if I could wipe away the mirage, it would show you what's really there. So I'm just going to go forward, and there it is. All right, so now, oops. So now, if I were to show you this picture and not give you, you would have no idea that 5 minutes before that this was complete. You would think that this is all water. Okay, so now we've had the mirage disappear and it fills in with what's actually physically there. So that's what happens in this image from Matthias KP. So I'm going to go back to that and come up here. Okay, so what we have right here is the mirage, and when I push play, if I'm at the right spot at least, when I push play, we're going to see that same wispy black line develop all the way across, and then everything that is below it turns into water. Here it comes, here it comes. It's right here. It's going to start going across. There it is, right there. It just jumped across right here. Okay, now all of this is going to disappear, Zach, and it's going to, and then it's going to be water. There it goes.
Look at that.
So now, when you see a boat over here, you know it's on top of the water. But 2 minutes ago, and you saw that happening, you would think that's over the curve being loomed up.
Mm-hmm.
So shout out to Matthias, because that's just beautiful.
Yeah.
You know, regardless of what we're doing, I mean, it's just beautiful as it is, right?
Yeah, thank you, Matthias, for just taking the time to get out there and do this stuff like you guys do.
I want to try to, how could I, is there a way to mark, Alexander, do you know if there is a way to mark this video with a...
Oh, I don't know it so well, sorry.
Yeah, I'm trying to see if there's like a tool that I can put in a marker here, because I want to watch this. I'd like to put a tool in, a marker at the top of the torso, at the horizon, and just watch this. Just kind of keep your eye at a spot and see if that thing changes height. It's going to be difficult because you're going to want to follow.
Oh, yeah.
You're going to want to follow it. Yep. That whole landscape. Look at that. That whole landscape.
Everything's moving.
Yeah. No one pays attention to that. No one thinks about that. But look at the same thing happens on this one, and maybe we'll wrap it up with this. The crazy ether. So it comes out here. I don't know. There it goes. Look at that. Like, how would you figure out like how much distance that is covering? Okay, so the thing about this is that if you play this at normal speed, you know, it's going one second, you're not going to notice that transition. After 10 minutes, like, I don't even know, let's go. All right, so this is going to drop down. Right? Okay, do you realize what that means physically about my lens? What would my lens have to be doing right now, Zach?
Jeez. To make that? I don't even know.
My lens would have to be rising up to drop the image. Just like in reverse. If this is where I started my camera, and then my camera wasn't tightened well enough, and so it started to drop, here's what the image would do.
Okay, yeah, I see what you're saying.
If my
yeah.
lens, okay,
The whole, everything's moving.
yeah, but it's also, but again, that would mean that my lens would be dropping down,
Yeah.
right?
Yeah.
But I'm playing this backwards, so then the opposite is true, because the aquascape is dropping. It would mean that my lens would have to be rising up, which is physically impossible unless I'm the one controlling it, and I have set my camera up, tightened the shit out of it, and pushed record. But look at this. The island in the background is dropping. This is absolutely just mind-blowing. You know? So tell me Alberuni went out and measured the horizon with his astrolabe.
Yeah.
Right? Whatever. Look at that. It's still doing it, man. It's still doing it. Now, what would be interesting is if I had another camera looking 10 miles south. You know, what's going on the horizon?
Like you said, yeah, we need 100 people out there.
We have the same effect going on.
To actually know what's going on, we'll need 100 people with all kinds of gizmos and gadgets and sensors and monitors, and that's why I gave up.
Well,
I got pretty far. I got to the point where I comprehend, you know, why things are happening somewhat the way they're happening. But as far as this stuff goes, man, you could spend a lifetime.
I mean, because look, you've got in this image here the entire. Okay, so here's the. Okay. All right, here we go. Let's go all the way back. Let's try to catch up. I don't know why it's not catching up. I can't refresh this. Let me switch from one to the next. All right, I want to get it to where it's a larger exposure. I'm just going to push play. Okay, so look at the legs, right? These are the base of the oil platform. It was pointed out the other day when we looked at this, SE Montreal, I can't remember if it was Alexander or SE. But you've got this lateral line here, mirrored down here. So if this is a mirror, you got to cut that in half. There's an inversion here, you can see. So you've got a towering of the legs, okay? Where are these legs physically? They're right here.
I reacted to you about it because in the distance, of course, the tower is just standing above the water. Yeah.
Correct.
But what we possibly see here is magnification.
Yeah.
And it's a miracle, but it's almost as if the reflection of the legs is shown in the mirroring, but because of the magnification that brings the horizon visually closer, and the part of the visually the tower above the horizon sinks low, yet the legs are visible in the miraging.
I see that.
Okay, so where was I before now? Going back up here. I'm gonna get to a point where there's no real mirage. Okay, so now the baller is going to say the base and the feet are behind the curve.
Yeah.
But it's right. They're all right here, just squashed to hell. Come on. Okay, here's the opposite. Okay, here's the opposite. Okay, where's this? 1650. If we don't have a problem with towering, this is not physical, right? We don't have a problem with that. Their question is, how can the legs be squashed to such a small space? The same way it can be stretched out like this. It's just the opposite. Come on.
Yeah, just like that big red line we saw on the building.
Yeah. Yeah, yeah.
It was real big and thick, and then all of a sudden,
okay,
it was thinner than the white line.
Okay. Let's go
Above
back.
it.
Yeah, yeah, let's go back.
Yeah, look how big that red line is right there.
Yeah.
Look at
Right.
that, how
Okay.
huge it is.
And now
Look at it.
look at that, right? So again, how can this section be squashed right here? Because that's what it is.
Mm-hmm.
Here it
It's
comes.
the same as the one on top.
Don't blink. Here it comes. Look at the one above it is growing. Look at that. Look at here it comes. Here it comes. And they're all proportional according to Matthias KP. So if they're all proportional, then there's 9 of them. 1, 2, 3, 4, 5, 6, 7. Right. So there's a section right here. I mean, I don't have a problem if these.
There may be one even up.
Yeah, yeah, yeah.
We can't see the top.
Right. But that's a demonstration of it right there. Like you have 75 feet squashed right here. Let's just say, okay, right? Here's 75 feet. This is 75 feet. Smashed to half the size of this. This is 75 feet smashed to what?
Third.
Yeah, a fifth. 20%.
One more.
You know,
Yeah.
whatever. Right? Yeah. Yup.
Amazing.
Good stuff. Good stuff. All right. Well, tomorrow's show, I'll do a show either way, but in the plan is that Pete Shea is going to be on, because Pete Shea, you know who Pete Shea is, Zach?
Yeah.
Okay.
Oh yeah.
He and I had a discussion on Ranties yesterday that we've had before, where he believes that the miraging that we're seeing right here is 100% on the water. It's all aquatic, and so we will have that be the focus of our discussion tomorrow.
I know they're going to be showing the house, having people come, and we're going to be going camping while they're doing this. But I'll get in touch with you next week when we get back. And if you guys haven't done the Wavy Road one yet, I'll jump in with you guys.
Okay, well, let's wait. If you want to do that, let's wait. We'll wait for you.
Okay, yeah. I know we won't be camping until the house sells. If it doesn't sell, we'll definitely be coming back. But yeah, it's just like a 3-day 4 excursion.
Sounds awesome, dude. Sounds
I can't wait to
absolutely
get back up to
delicious.
them.
Oh, man.
Yeah, let's do that. Okay, let's do that.
Alrighty. Well, Alexander, it was a pleasure meeting you, man. Thank you. You made my day. You have no idea.
Okay, Zach,
You did.
you deserve it.
Travis, always a pleasure, brother.
Yeah, thank you, Zach. Thanks, Alexander. You guys are the backbone of all of this discussion, so thank you so much.
Okay, thank you. Bye.
Bye. All right, everybody out there in the Plain Truth Land, I have been your host, Travis Finley. This has been another exciting adventure of Coffee Sodes. Until